So let's talk about some fundamentals of approach in math. One of the most important ideas to understand in math is the idea of deductive reasoning. This is the idea that there are certain assumptions that lead to certain conclusions, and importantly, if the assumptions are true, then the conclusions must be true. So critically, we're not talking about a correlation. When the assumptions are true, then generally the conclusions usually true. Anything like that. We're talking about it must be the case that the conclusions are true if the assumptions are true. So this is called deductive reasoning. And this is one of the deep underlying ideas of how math is done. If the assumptions are not true, right? If any of the assumptions fail to be true, then you can't conclude anything. Right? So deductive reasoning critically relies on all of the assumptions being true. Okay, now, so how does this show up in math? Well, we talk about things called theorems. And a theorem will usually be stated in something along these lines. There are certain assumptions that will be phrased as conditions in the theorem, and then you get a conclusion, which is the result of the theorem. So this is how a theorem will typically be stated. If conditions, then result. Okay. So what is a proof of a theorem? The idea of a proof is it's deductive reasoning from which you start with your assumptions and get to your conclusion, namely your result. Now notice there are assumptions that you can make that are more than the conditions that you've explicitly listed. So in particular, a theorem will usually be stated using certain words. Those words have definitions. Those definitions are strict terminology rules. What exactly do these words mean? And if a theorem is stated using those words, then you might have to go back and make a reference exactly to what that word means. So you're allowed to use that in a proof. You might need to make a reference to a previous theorem that's already been proved. And that's also perfectly fine to use in a proof. There are also things called axioms. We won't be making any use of axioms in Math216, but the idea here is that these are fundamental assumptions at the very bottom of math. All of math is built up on top of these axioms, and in a class like Math216, we just won't be getting that rigorous, where we delve down to that level at all. But nevertheless, they are there, and there are assumptions that can be used in a proof. Okay, so this is a long and interesting discussion that we won't get into in Math216, but exactly what those axioms are is very interesting, but it's mathematicians are very careful about exactly what are axioms, and again, we won't be doing that in Math216. Definitions are very carefully chosen. What words mean is extremely important to be precise about, and so those definitions have to be adhered to strictly. Proofs must be very careful and rigorous. So let me show you an example of a theorem. Here we go. So here's a theorem. If you have a prime number greater than 1, then the square root of that is not rational. So this is a theorem. All right, now in order to prove this theorem, I have to be clear about, wait a minute, what does this word rational mean? So you'll notice up here I have a definition of rational. The number is rational if it's the ratio of two integers with no common factors. Okay. All right. So I'm not going to go through all of the details of this proof. This is not really Math216 relevant, but this is a really interesting result, and it's not a hard proof to write down. But you'll notice in a couple of places how this relates to the previous discussion. So we have a theorem with conditions and a result. The conditions are here. The result is here. You'll notice that I make use of a definition in the proof, and here it is. I'm making use of the fact of what this word rational means. So I'm taking this and making use of it and interpreting the word rational. Now you'll notice I'm doing a proof by contradiction here. I'm trying to prove that the square root of p is not rational, and I'm going to achieve that by supposing that it is rational and then deriving a contradiction. So that's how I get to this assumption that the square root of p is rational. Okay. All right. Now there is something else to point out in here, and that is how the condition shows up in the proof. So where in the proof here do we use the condition? Where do we use the fact that we are assuming that p is a prime number? And if you look through here, it doesn't leap off the page at you exactly where it is, but here it is, in this spot in the proof here. The assertion is that if p is not a factor of this number m, then it's also not a factor of the number m squared. And if you think that through a little bit, you realize that p does have to be prime for that to be the case. So think about, for example, let's think about p being 9. All right. Well, 9 is not a factor of 15. But is 9 a factor of 15 squared? Well, if you think about it, 15 squared is 3 times 5 times 3 times 5, which is 3 times 3 times 5, which is 9 times 25. So p is not a factor of m, but it is a factor of m squared. So the point there, the thing that makes that go wrong, is 9 is not prime. Okay. So other details in the proof here, and you guys can read this on your own. This material here is not Math216 relevant. I just wanted you to see how these different things combine. You know, where a definition gets used in a proof, how the conditions imply the result, etc. Okay, and then also notice that the argument here is very detailed and strict. Okay. So I want to say a few things about misconceptions about deductive reasoning and math in general. And I have a few of them listed here. Let's start with the first. Here's a misconception. Many students are not clear on the difference between a definition and a theorem. And they are importantly different things. So let's come back up here to our little road map. And you see a theorem is a statement. This is an assertion of a true fact. A definition is a choice. It's just terminology. It's an arbitrary decision that's made just to help you have some words to use in discussing what it is that you want to talk about. Right? It's not a statement of truth. It's just terminology. A theorem is a statement of truth, that if this is true, then that result must be true. So it's an actual assertion. So these are very different things, and students very often have difficulty seeing the difference because they both just kind of look like statements about math. This appears to be a statement about math, and this appears to be a statement about math, but it's important to realize how very, very different they are. This is just putting a label on a concept. There's no mathematical truth that's being asserted here. Whereas here there is. Okay, so that's an important thing to understand. Now, I do have to acknowledge that there is an awkward situation that can arise, and that is the idea of equivalent definitions. So, for example, here is a definition of the number e, Euler's number. You might have seen this in a single variable calculus class. Here is a different definition of the exact same number e. So these are two different statements, but as it turns out, the number that is defined by this equation is the same as the number that is defined by this statement. They happen to give you exactly the same number. So if you define e to be this, then you can show that e then has this property, and vice versa. If you define e to be the number that has that property, then you can show that e has that property. So we call these equivalent definitions, right? Importantly, though, when you're doing math, you have to choose one of them to be the definition and to work with. You know, that's your fundamental definition of that object or word or what have you. And then the other you take as a theorem. So, for example, I might define e by this, and then at that point, this becomes a theorem about the number e previously defined. Okay. Second misconception. Now, I have to admit I've never actually heard students say this, but I see students acting as if they believe that conditions don't matter, or you don't have to bother checking conditions, or, well, they're always true, why would I bother? I mean, certainly you see students very often simply glossing right over conditions on a theorem. Well, that's absolutely not okay. Let's look at this theorem here. This theorem here has a condition, P must be prime, that is required for this conclusion to be true. So again, think about the number 9, right? If I just kind of gloss over the fact that 9 is not a prime, if I don't check that condition, then I'd go straight to the conclusion that says, hey, square root is not rational. Well, that's not true. The square root of 9, definitely rational. In fact, it's an integer. Right? So it's important to realize you only get to use a theorem, you only get to cite the result of the theorem if, in fact, you have checked the conditions. There might be more than one. But you do have to check those conditions, and only if those conditions are satisfied do you get to use the theorem. Okay, and here's another sillier condition example down here. Okay. So let's talk about what deductive reasoning has to do with science and statements about the physical world. Very commonly, students talk about proving statements about the physical world, proving things in science. And certainly, there's a lot that you can do in science to learn things about the physical world, to come to understand the physical world. But it's not deduction. It's not deductive reasoning in the mathematical sense. So now here is a deductive relationship between theory and experiment. If a scientific theory is true, then it is true that the experiment will work as the theory predicts. Right? I mean, that's what a scientific theory does. It makes predictions, and if it's true, then those predictions should work. But that only goes one way, and it's important to acknowledge that this arrow is a one-way arrow, and you cannot turn it around. Right? It's not the case that just because the experiment worked as predicted, that does not imply that the theory is true. Right? And here's a simple, classical counterexample. Let's think about gravity, and let's think about the very long believed but false suggestion that heavier objects fall faster than lighter objects. Right? Well, we can imagine the following experiment. Imagine that you go to the top of a tall building with a cannonball and a feather. Right? And now the cannonball weighs more than the feather, and so this theory predicts that the cannonball will fall faster than the feather. And sure enough, you drop them both off the side of the building, making sure that no one is below, and the cannonball falls much faster than the feather. So in that situation, we have a silly situation, but in fact that experiment did work exactly as the theory predicted. But that theory is false. Okay. That's a coincidence having to do with air friction. Okay. All right. So here's something that is deductively legitimate, allowing you to draw a conclusion about a theory, and that is that if the experiment fails, well then absolutely that theory is false. Right? And so here's an example of that. Let's think about, again, objects falling. And let's think about now, instead of a cannonball and a feather, think about a cannonball and a baseball. Well, go up to the top of the building. The cannonball weighs much more than the baseball. The theory would predict that the cannonball would fall faster. And you drop the cannonball and the baseball off the side of the building at the same time. They hit the ground practically at the same moment. That is not what the theory predicted. The theory predicted that the cannonball would fall faster, but they didn't. So the experiment failed. Right? And from that, we can then conclude that that theory, the theory that heavier objects always fall faster, that theory is false. Right? So this is legitimate deductive reasoning. This is not. Okay, so it's important to see the difference. All right, so how can you ever prove a theory to be true? What you notice here is that what you can prove deductively is a conclusion that a theory is false. So we can disprove scientific theories. So how do you actually make any progress in science? Well, while you can't deductively prove them, what you can do is view them as being stronger by surviving more and more experimental challenges, right? So the idea is every time you do an experiment, then there's the possibility that that experiment will prove the theory false, right? And so the more times that the experiment does work as predicted, and by more times I mean the more different ways, the more different tests of the theory that the theory survives, right, then the more likely it seems that the theory might be true. Right? It's important to realize, though, that this never really proves the theory. A great example is Newton's theories of motion. So Newton's theories of motion were proposed in the mid-1600s, and 250 years later, Einstein came up with a theory of relativity, and experiments that would have been absolutely impossible in Newton's time, to be fair to Newton, showed that Newton's theories of motion were not quite exactly correct. They were very close for low velocities, but not correct, very importantly. Okay. All right, so said differently, Newton's theories were only tested in certain ways. They were tested in the only ways that were available, again, for 250 years, but all of the ways that were available had the common feature that they didn't involve very fast speeds. And so they were never, Newton's theories of motion were never tested in the way that that would have proved them wrong. Okay. All right. So let's talk about mathematical modeling now. Mathematical modeling is something that's relevant to science. I mean, a lot of what science is creating mathematical models that describe the world. And yes, you can do deductive reasoning within that model. Absolutely. So a mathematical model makes assumptions about the physical world. This is the mathematical model. You thus turn the the physical world into sort of an assumed math problem, and you can do deductive reasoning within that mathematical model, and you get then conclusions of the mathematical model. But keep in mind, even if the conclusions of the mathematical model are verified, it does not go backwards to prove the assumptions that you've made about the physical world. So you just have to keep in mind that's what mathematical modeling is, and you cannot prove the assumptions that you're making in the mathematical model. All you can prove, you can make deductive conclusions that are true within that mathematical model. And if it's a good mathematical model, then it will model the physical world well. But again, you're not deductively proving things about the physical world. Okay, so in Math 216, it's important that students understand these basic ideas of reasoning that are used in math. And keep in mind, this is not a science class, this is a math class, and so students will be expected to adhere to deductive reasoning. We are doing deductive reasoning in this course. That's our primary interest. And I will say, to a degree appropriate to the course, so we will not be demanding a level of rigor and precision that would be, for example, appropriate to Math 431. That's a much more rigorous math course, and this will not demand at that level. On the other hand, it will expect more than in Math 212. There's definitely more rigor and more proof and more abstraction in this course than in Math 212. Exactly how much of a degree we have to communicate with context. So you'll see examples in the lecture notes, in the book, looking at my old exams. These will all be examples of the kind of level of rigor that we'll expect in this course.